So in this video, we're going to go over a continuity theorem for integrals, which is weaker than the fundamental theorem of calculus, and you'll see by the end of the video that that weakness is in fact necessary. So I fix a function little f from the integral ab to r, and I assume that f is integrable, and I define a function big F by this formula here. F of x is equal to the integral from a to x of little f. Okay, so this is of course the thing that we're used to seeing from the fundamental theorem of calculus. Then the conclusion of this theorem is that capital F is in fact continuous, which of course is weaker than the conclusion you might be expecting. All right, the proof is fairly short. I define m to be the supremum of the absolute value of f of x for all values of x that occur in the integral ab. And I claim that that's finite. Actually, I'm not proving anything there. That's part of our definition for integrable, is that the function f must be bounded. Okay. Now I'm proving continuity, so I'm going to fix some epsilon greater than 0 and give a delta. And in fact, since f is going to be continuous on a compact region, there's just going to be a single value of delta, in this case epsilon over 2m. Now I'm going to fix a pair of points, x, y, so that x minus y is less than delta. Sort of the next step. In this particular case, it's easier to think about values of x, y, where x is less than y separately from values where x is greater than y. Just because the next part of the argument is a little bit easier to write down, but that's not going to fundamentally change any of the calculations. So what do I have in this situation? The absolute value of capital F of y minus capital F of x, just by definition, is the integral from a to y of f minus the integral from a to x of f. And now we're going to do a bunch of calculations which are probably familiar, but which we justified in the last video. So that's equal to the integral from x to y of f. Why is that justified? Well, we had a linearity formula for integrals, and we could use that formula as long as all of the integrals that show up, this one, and this one, in fact exist, which is the case here. That value there, the absolute value of the integral from x to y of f, is less than or equal to the integral of the absolute values. Again, that was one of the lemmas that we saw in the last video, and it holds since all of the integrals of interest exist. And then finally, we can replace an integral of a function by an upper bound on the function itself. So I replace absolute value of f just by m, and I get this bound here, and by my choice of delta, this is equal to epsilon over 2, which is strictly less than epsilon. Okay, so I did only one case here, when x is less than y. The case that y is less than x is essentially the same, and we end up with exactly the same bound there, which completes the argument. Okay, so that's it, a fairly short proof, but using essentially all of the lemmas that we proved in the last video. The one comment really that I want to have here is, you're used to seeing something much stronger here in the fundamental theorem of calculus. Now we will get to the fundamental theorem first, but I want to comment on this, that actually this function capital F doesn't have to be differentiable, and there's sort of a simple counterexample. I define little f to be 1 for 0 less than x less than 1, and minus 1 for 1 less than x less than or equal to 2. Okay, so in other words, my function looks like this. And in that case, capital F of x, you can compute. I'm not going to go through all the details. And what you end up with is this pyramid-shaped function over here. And in particular, there's a point up there where the function is not differentiable, even though you can see that it's continuous. Okay. The one last thing that I wanted to mention here is that this function here isn't differentiable, but it's a very mild form of differentiability, of a failure of differentiability, right? Sort of have this problem at this point where there are a couple of linear approximations, or rather uncountably many of them, but that's really the only thing that happened. And I'll point out that actually that's in some sense the worst thing that can happen, because we actually proved quite a lot more than f being continuous. We actually proved this type of bound here, f of x minus f of y in absolute value is less than or equal to capital M times x minus y. In other words, there's this linear bound, m times the absolute value of x minus y, on how much f is allowed to change over some small region going from x to y. So this type of bound is called Lipschitz continuity. It's much, much, much stronger than being merely uniformly continuous, and all functions f of this form have that extra property. Okay, so it is true that in fact the integrals of functions f really are nice functions. They're not just continuous, they're better than that, but they're not necessarily quite differentiable. Okay, that's it.